Okay, so just a minute. Let me re-share my screen. Okay, I have completed discussing the halt instruction. Okay, now okay, I was also discuss. I have already discussed about this DI instruction. So we were talking about interrupts, that we are having this interrupts trap RST 7.5, 5.5, 6.5 and INTR. And when we were discussing the interrupt of 885, I have already told you that the trap is only an interrupt which is non-maskable. Means you cannot avoid this trap interrupt. Okay, so all the other interrupts you can mask it out. Means let's say that you are performing some critical task and you don't want to get interrupted. Okay, so at that time you will be masking yourself. It is the same case as you are appearing for the examination. You will be turning your cell phone off so that you will not get interrupted. So you are masking it out. That is what we call it as a masking. Okay, so all the rest 7.5, 5.5, 6.5 INTR, they are maskable interrupt, and trapped is non-maskable interrupt. So you can mask that interrupt by executing this instruction DI. So generally what we used to do is, okay, if we are in interrupt service routine, and if that is very important, then we would be disabling all the interrupts, okay, by executing the DI instruction. So if you execute the DI instruction, all the interrupts would be disabled. And then to enable an interrupt, we use EI instruction. So EI instruction will enable the interrupt. Okay, so this instruction is necessary to re-enable the interrupts except trap. So if you want to reinitialize all the interrupts, okay, so you can use this EI instruction. Like, the second is seam instruction, set interrupt mask. Okay, now you don't want to disable or enable all the interrupts at the same point of time. You want to control some interrupt. Okay, so that can be used with help of seam and ream instruction. Okay, so the seam is a multi-purpose instruction that is used to set the status of interrupt 7.5, 6.5, 5.5, as well as to set the serial data input bit. Means already we have already seen that there is SI and SO. There are two pins we use for serial communication. Okay, to set the bits we would be using this SIM instruction. So this instructions load the 8-bit data into an accumulator with the following interpretation. Okay, so you can load this accumulator by this interpretation. Means if you want to mask the 7.5, 6.5, 5.5, you can set any bit to 1. Suppose if I'll set the 2 bit of my accumulator to 1, and if I execute sim instruction, then it will mask my 7.5 interrupt, but 6.5, 5.5 will not be masked. Okay, this it will set the enables if it is 0. Okay, and bit 0 to 2 are ignored if this bit is a 1. Okay, means this is just for enabling and disabling all the interrupts. So if it is 0, then bit 0 to 2 means 0, 1 and 2, they are ignored. And if this is equals to 1, then mask is set. Okay, so if this bit is equals to 0, then there is no use of this. But if you want to mask any of the interrupt, you need to put over here 1 and then set the other values. Okay, now d4 bit is to reset our 7.5. Okay, if d4 is equals to 1, it will reset the 7.5. d5 is not being used, and d6 is to serial data enable. If d6 equals to 1, bit d is output to SOD Lect. Okay, so this bit would be output to the SOD. Okay, serial out data. Okay, so this is the interpretation. Means if you want to have this masking, or if you want to send the data serially, then you need to execute every time a sim instruction. Okay, so what you can do is you can load your accumulator with what the data you want. Suppose 08 means 0000, 8 means 1000. Okay, so that means you are enabling all the mask. Okay, I think all of you got it. Yes, you need to load the value into an accumulator with whatever the interpretation that we have seen over here. For masking this, you need to set it to 1. You need to set this value to 1 to make all this 3 bits enable. You want to reset our 7.5, then this bit would be set to 1. This is unused, and for serial data enable, you need to make this as 1, and whatever the data you want to send to serial output, you need to get that value over here. Okay. So the other instruction is a ream instruction, that is read input mask. So whenever you will execute this instruction, your accumulator get value loaded, and you can see the value with the following interpretation. Okay, so yes, so to read the interrupt mask means this would read the interrupt mask. Okay, which are the interrupts which you have masked or not. Okay, this would read the interrupt enable flag, whether the interrupt is enable or disable. This three, I7, I6, I5, this will be identifying the interrupt, means whether the interrupt is pending or not. Okay, so this will identify that which interrupt is pending. Suppose if any value is set to 1, you will be assuming that this interrupt has occurred, but still it is pending. Now pending means what generally we used to do is so if there interrupt occur, then your program counter will be loaded with the predefined value if your interrupts are vectored interrupt. Okay, and at that location you will be writing down the code for the interrupt service routine. Now if you provide the service routine to that interrupt, okay, then it would be not in pending state. But if the service is not being provided to that interrupt, the interrupt would be in the pending state. So this particular thing will help you to know whether the interrupt have been given service or it is in pending. And this particular bit, it will receive the data serially, means whatever the data available at your SID, that would be available in your D7. So to read the interrupts, whether the interrupts are pending or not, or to read the serial bit data, okay, you are supposed to instruct the execute the ream instruction. Okay, so let's see. Addressing modes, so we will be quickly discussing that what are the different addressing mode in our 8085. Okay, so there are immediate addressing mode, direct addressing mode, register addressing mode, indirect addressing mode, implicit addressing mode. So these are the 1, 2, 3, 4, 5 different addressing mode in our 8085 microprocessor. Let's see what is immediate addressing mode. Okay, so uh, if I write mvib 20h, it is immediately added, means all the instructions would be ending with I. CPI 68, SUI 30, ADI 45, LXID, MVIB. Okay, all these are what we call it as an immediate addressing mode. You will find it out that immediate value would be loaded into the register, or the processing would be done. Means if it is ADA, SBA, CPI, it would be in relation to your A register or accumulator. The other we called it as an direct addressing mode. Okay, so these are some of the example of direct addressing mode. Means LDA 1035. So you are directly pointing out the address. Okay, and whatever the content of this 1035 is, it will be loaded into your accumulator. Okay, so here 1035 is in 16-bit address, memory address. Okay, so it is what we call it as a direct addressing mode. And these are the two IO devices that we talked about. Means in 02 or out 03. Register addressing mode, or it is also called as a register pair. Okay, that contains the data. So MOV A comma B, add B, DADH. So all these are what we called it as a register. It means you are using a register for accessing the content. Okay. Now there is another mode we called it as an indirect addressing mode. Okay. So indirect addressing mode means LDAXD. So indirectly you are getting the value from your DE register. Okay. So whatever the value which is being pointed by your DE register would be stored into your accumulator. So this is what we call it as indirect addressing mode. LDAX, STAX, they are the example of the indirect. And the other is implicit or implied addressing mode. Okay, so this mode doesn't require any operand. The data is specified by the opcode itself. Means, for an example, XTHL, SPHL, PCHL. I think I have discussed all these instructions. So over here you will not be requiring any operand. You directly means HL pair would be loaded into your stack pointer, HL pair will be loaded in your program counter. So this is implicit. Okay. So I'll be skipping this assembly language program part at this point of time. I'll be discussing it later on. It means the next class I'll be discussing. But I would like to discuss this timing and machine cycles. Okay. So timing, it's very important. Means you need to always keep a track that which instruction the microprocessor is executing. Okay, nowadays we are having an operating system that would be doing all the things for us, but previously we were not having an operating system. Yeah, the programmer needs to keep a track of everything what the CPU is doing. Okay, so at that time it is very important to know the timing and what the machine cycle of your 885 instruction is. Okay, so already we have talked about what is T state. Hello, what is T state, a machine cycle and an instruction cycle. Already we have discussed that thing. Okay, so generally the timing cycle required by 8085 microprocessor are this. Means if the operation is opcode fetch, it requires 4 to 6 T state. T state is nothing but it is one clock. One clock equals to one T state. Okay, memory read operation, whatever the memory it may be, it will require 3 T state. Memory write, it will also require 3 T state. IO read, it will require 3 T state, and IO write, it also requires 3 T states. So some of the instructions which require 5 T states are halt, and some of the instruction which requires 6 T states, they are call, conditional call, DCX, INX, PCHL, SPHL, push, or conditional returns. So all this instruction will require 6 T states. Okay, except all they will require 4 T states, and only the halt instruction that will require 5 T states. Okay, a machine cycle. Okay. So fetch is one machine cycle, memory read is one machine cycle, memory write is one machine cycle, IO read is one, IO write is one, and read immediate data will also require one machine cycle. Okay, so let us see the timing diagram of the instruction move B comma D. Means the content of D must be stored in the register B, and if you remember, this is 1 byte instruction. Okay, so in this these are some of the thing that would be done. Means first thing is it would fetch the code, so it will require one machine cycle, and the timing for it is 40 states. Now if it is MVIC 17, you know that this is 2 byte machine cycle, sorry, 2 byte instruction. So for that it will require one machine cycle to fetch the opcode. We already distinguished that this MVIC is your opcode and 70 is your operand. Okay, so one machine cycle is required to read fetch the opcode, and the other is required to read the content. So actually it requires 2 machine cycles. Okay, and if I'll go for the timing, fetch will require 40 states and read operation will require 3 T states. So in all it will require 70 states. Same is case with sorry, this is something different because it is based on your HL pair. Okay, so it is MVI M25H. Okay, so over here it will require one machine cycle to fetch this code, okay, one to read this operand and the other one to write the location, okay, because m is nothing but it is the location which is being pointed by the HL pair. So you need to write this value 25 into that particular location. So one is for fetching the opcode, the another is to read this data, and now this data is supposed to be written into your memory. So one machine cycle will be required for writing the data. So in all it will require three machine cycle, one for fetch, one for read, one for write. So three. And if I'll go for timing, 4 T states would be required for fetching the data, and 3 T states for reading the data, and 3 for writing. So in all, this instruction required 10 T states. The same is case with your move m comma a. So in this the opcode would be fetch and then the memory would be read. So it requires two machine cycle and 70 states. Same is case with your move m comma a, fetch the data and write the data. So 70 states. NOP, it only requires one machine cycle and it required 40 states. Halt instruction, okay, it will fetch and wait. Okay, so it will fetch the opcode and one machine cycle is to wait. So that's why it requires 5 T states. Okay. In 18, it will fetch the opcode, read the data and read your IO. So it requires 3 machine cycles. Okay. Definitely I'll be showing the timing diagram of it, but this is how you can calculate that how many number of T states are required for executing a particular instruction. Same is case with out. It will again require 10 T states. If it is add, it is one machine cycle instruction, 4 T states. ADI, it is two machine cycle, fetch plus read, so it requires 70 states and so on. Okay, so let us try to see. So this is how you can, okay, this is LDA 2030. One is to fetch the opcode, the second is to read the lower byte, the third is to read the higher byte, and then read the memory, which is 2030. So 1, 2, 3, 4, 4 machine cycles would be required, and you can see that 13 T states are required for low LDA instruction. Okay, so now let us try to see the machine cycles. And so this is just an exercise you can perform to find it out that how many number of machine cycles timing, what is the size of this instruction, what is the timing in a machine cycle. Timing diagram. Okay, so we talked about all this thing. So now let us see the timing diagram, that what particular time what thing is going to happen. So always you will find it out that the first machine cycle is for opcode fetch. Okay, and it is having 4 T states. Okay, so let us see how all this the opcode is being fetched into your CPU. Okay, so each T state we find it out that each clock pulse, okay, it is of 1 T state. We consider it as an 1 T state. Okay, now whenever you fetch the opcode, the first thing is you need to keep the data, sorry, you need to keep the address onto the lower byte, sorry, higher byte, higher memory location address into onto the line 8 and 15. Then you will place the lower byte of address or lower order address in AD0 to AD7, and then you will make your ALE 1. Okay, so address latch enable. Have I discussed address latch enable? Hello? Hello? Hello, are you all there? Hello? Hello, 27 number. Have I discussed ALE, address latch enable?
Yes,
27
sir.
number, are you there? Okay, so
Yes,
you are
sir.
no, You are knowing what is address slash enable. Okay, so as this AD0 to AD7 they are used in multiplexed form. When to find out data, when to find it out address, that is being specified by your ALE. So ALE will become 1. Your address are available, then your memory is supposed to be read by making IO or memory bar. Memory bar means you are going to read your memory. Okay, and whenever your read signal will become 0, okay, whatever the opcode is, that would be read into your CPU. Okay, this is opcode fetch. The second is memory read. So in that memory read only also we require 4 T states. Okay, so address would be capped, higher lower ALE same. You will make your memory ready. Okay, but at the same time you will keep your s1 equals to 1, so you will be reading the memory. Means already we have discussed that if s1 equals to 1, s0 equals to 0, and if io slash m equals to 0, it is memory read operation, and then you will read the data from your memory. Same way memory write is also being executed, but at that time you will make your s0 1 and s1 equals to 0 and m0 equals to 0, and you will write, means write bar is being made 0, and whatever the data available onto your data line, that would be written into your memory. IO means it would be same as what we are going to do for memory. The only difference is now your m1 equals to 1 and s1 equals to 1, you are going to read. Same way write operation, all the things would remain same, the only write signal will become 0. Now let us see the timing diagram of move instruction, move b comma a. Okay, hello, hello, am I audible to everyone?
Yes, sir.
Yes, sir.
Yes, sir. And is my screen visible to everyone?
Yes, sir.
Okay. Um, So we have seen that how memory is being read, how memory is write, how opcode is fetched. Now let us try to see all the things together. Uh, just a minute, I lost my window. Okay, let us do one thing. We would be keeping this thing to be discussed in the next class. Okay, so if you are having any kind of doubt up till now, what the things I have discussed, you are free to ask. We would be discussing the timing diagram of move instruction and the other instruction in the next coming class, and in also we will be discussing about the assembly level programming. Okay. So is there any doubt up to the things that I have discussed up till now? Hello?
No, sir. Not up to now.
Okay, fine. So see you in the next class on Monday, and we'll be discussing the rest of the things which are left in the quiz class discussion. Okay, fine. Thank you.
Thank you, sir.